Hello, welcome to SUSECON Digital 2020. My name is Ralph Dannert. I'm a systems engineer with SUSE, and my co-presenter and chief architect of the solution at Knorr-Bremse is Adalbert Schuster, administrator. So in this session, what you will learn is Raspberry Pi in a factory environment, and you will get to know in this session how the solution is used, what needed to be done with the Linux environment, how to configure it, what obstacles were there that needed to be removed, and also how it is used in the factory themselves. So who's Knorr-Bremse? Knorr-Bremse is a German manufacturer of braking systems mainly for trucks and for rails. So although Knorr-Bremse is not widely known, and that's mostly because it's manufacturing parts that are used by other big companies like car or rail manufacturers. For example, ICE trains use the brakes and other trucks. So Knorr is active in 30 countries worldwide, has nearly 30,000 employees, and the main usage of SUSE at Knorr-Bremse is SLES for SAP with more than 250 servers. There are also some other technical applications, but we will also have Raspberry Pi with SUSE. And with this, I'd like to pass it on to you, Adi.
Thank you. Welcome, ladies and gentlemen. Here on this picture, you can see the complexity of a modern brake system. It does not only consist out of driver's pedal, disc and pads. There are further functions like front and rear cameras and radar for distance warning and control, pedestrian and bicycle detection with driver warning, automatic brake and so on. On the right picture, the photo shows a simulation of an extreme situation in one of our test areas with truck is stabilized and trailer is not. And if you see the big side wheels, it is because we do not want to lose many trucks and trailers for this experience. Next picture, please. This is the IoT design. Let's have a look into a factory producing these mechanical components. Before IoT, some guys walked through a factory and manually collected data on paper. Our goal of the IT is to get automated real-time information to the place where it is needed. This may be workers, factory management, SAP production planning system, and so on. Therefore, the IoT system, in our case ThingWorx, was set up. The edge computer is collecting data from a factory, adding the meaning, and sends it to IoT server. On the bottom side, we have the easy part. It is a small edge computer, Raspberry Pi, which is fetching machine data from over a network, translated to ThingWorx and sent to ThingWorx. But there are more complex situations with older or non-network capable signal sources, like push buttons for acknowledging something, sensors, for example, if a part passes a certain position, readers for barcode, RFID, badges. For all that, a multiple purpose card from Automatisierung Dresden is used. Next slide. Here you can see a screenshot from a Hungarian factory. This is the worker's view directly connected to a Raspberry Pi edge computer. The information here is things like number of produced parts, time to next part exchange, time to next cleaning cycles, and pure worker information. Next, please. Here can we display in the factory control office. a visualization of IoT sampled data. We have red lights on problems, a graphic state analysis shown here, actual versus plan, and on the top left there's a production plan with red light steps showing the problem, and below a part of the assembly manual page showing the step with a problem to accelerate problem detection. And sorry for unreadable plans here, it was wanted so. Next slide, please. For multiple, let us have a look to the edge hardware. We have a multiple I/O board from ADG used for all signals we cannot get over the network. This card has a wide range of input voltage, maybe but battery buffered, is also supplying the Raspberry over the GPIO plugs. So we also can avoid this unstable micro USB power supply plugs on the Raspberry. And the GPIO is working in serial bus mode to accelerate it a bit. Binary and relay input and outputs are on this card. Analog I/O, RS-232 plug for barcode readers, and the card is capable to be cascaded. And as Knorr-Bremse made a rather good experience with ADG, so this card was wanted by our digital manufacturing teams, and this was given for me. Next, please. The Raspberry Pi is a second core component, and a MESkit is both plugged together. So for the Raspberry, there's a question, why do we use SUSE instead of Raspberry rather? Yeah, from SUSE we get a clear release strategy, which we need for our plannings. We get a good support with tested patches, because we do not want to operate our own test lab. We need a configuration management. SUSE Manager is already in place, and we have it, we can use it as the same way we do it for SAP. And we can use our assign support engineer for Raspberry questions too. And by the way, we use SUSE 15 Service Pack 1 because it's much more handy than the earlier Raspberry versions of SUSE. And for this, we replaced all SLES 12 by SLES 15, even if our SAP is still running on 12. Next slide, please. The Knorr-Bremse implementation is nearly the same as the primary idea was, but we added SUSE Manager here. The MESkit is used in several versions, in a box containing the Raspberry and with ADG board, or where we have only to fetch signals from a network as a standalone Raspberry Pi and sending data to the IoT. A monitor is not plugged to many devices. A keyboard is sometimes used. A mouse or a touchscreen acting as a mouse, yeah, also sometimes. So we must work with this, and we must support all these versions in a stable way. Next slide, please. This is the hardware of a Raspberry Pi. Let's have a look at this the Raspberry, our ADG card. All connectors are easily to get. We can connect very easy with cables. And on the top, we have a flap for changing the SD card. And the metal case is also used as an electromagnetic shield, so Wi-Fi is not good to use. Ralph, it's your turn.
Okay, so the main question really is how do you fit 1 gigabyte of usage of a standard Linux system into 1 gigabyte Raspberry Pi, or even more than 1 gigabyte usage. So we are using the Raspberry Pi version 3, and you only have 1 gigabit of memory. So this limit is really a challenge, and you have to take care that all the components fit into this. So here are some of the components we use in the setup. One is Windows Manager, ICE Windows Manager, that is used, which is known for speed and simplicity, and is used in also in lightweight Linux distributions, for example. So it's an X window system. It's also a floating window manager, so opposed to a tiling window manager. And within this, we only use 1 virtual desktop or workspace. And this is, for example, necessary because if you have a factory worker which is using his application and inadvertently gets into another virtual desktop, you don't want to have this. He will not get back, and the whole application is mixed up. So only 1 virtual desktop. And also, you can't use a standard web browser like Firefox or Chrome because they're much too memory hungry. So what we used here is Midori, which is meanwhile a part of SLES, but at the time it was still in Package Hub or in the Open Build service, and nowadays it's a standard component. So it was also not a how do you say, it needed some testing that all the applications worked well with Midori, but now it's really working well. So what else? To have a memory saving code, ADG already, they're coding in C, and they made it really not so memory hungry, so it wasn't using too much memory, and so that everything fitted into it. So what else do we have to, what else? Yeah, we have to make sure that there's enough swap space available, and this can be configured also during auto login for the Linux system. So another technical challenge is really that we don't have a real-time clock, and so what do you do? The clock is really set to the build time when the image was built. So one of the first things you have to do is really to set the real time early on. And for this, a cronid is used. And you need to pass the iburst parameter in the cronid.conf, because this is actually setting up the initial synchronization. It speeds it up a lot. And we will later see this is also queried to make sure that we have the time ready. So next slide. So what else? In the factory environment, you also have to avoid the vibrations, which is not totally possible because, well, we're in a factory. Although it's in a Schrank, we say, so I don't know, in an enclosure, yeah. And like you mentioned, Adi, before, like older micro USB slots, they can really be not working well and don't have a stable connection. And other issues might be that the temperature is much too high, and when the temperature is too high, the Raspberry Pi will clock down, and that's also not a good thing because the Raspberry Pi gets slower. So one thing you could use is really use heat sinks. They are generally available, but mostly they are glued and not screwed. So this is also not an option that you could use here. So finally, the command we see here, that's like, so it's a monitoring capability that you see here, because this command is executed via a salt command within SUSE Manager on regular intervals to measure the temperature. And with this, you have a possibility, yes, to monitor if everything is okay with the hardware. Yeah. So there was one thought also to use a standard monitoring solution like Nagios, which is in use at Knorr-Bremse, because we mentioned it's 250 SAP servers and they are monitored with Nagios. But it's really difficult to use it in a factory environment, on the LAN, where you have to open ports, and you just want to avoid that. So other things that are required from the factory. So it's really, no one really wants to boot a MESkit device. Yeah, no, they don't. Also, they don't want to shut it down. They don't even want to know that it's a Linux system at all. All they want to have is just some application they are familiar with that is showing up correctly in the display, and it needs to be there right away. No user login, nothing. Yeah. So you would say, okay, these are standard things that can be done, but you really have to make sure that it's a foolproof installation routine, which cannot be screwed up in any way. Also, no downtime is accepted. It needs to be very safe against power loss. So what was really needed to extend this boot process? So one thing is, like we mentioned, you need to apply patches at boot time, because no one will patch this device. And you also need to make sure that the auto login mechanism does everything you want to have. So we just see this in a moment. So how does the patch at boot really work? Yeah, so it needs to be stable and reliably continue to delegate everything to start the desktop. And it also can only start when cronid has done its job. So you need to make sure that the time sync is already correct. And after that, you will really see that SUMA, it will ask the SUMA, so SUSE Manager, for patches that can be applied then. Another thing that you have to avoid is really to use more than 3 reboots. It's only 3 boots are possible to avoid a reboot loop. And so afterwards you have the problem that you have a machine that is not patched correctly, but there Knorr-Bremse uses a trick. For example, you can find out that the system is booted, so it has a short uptime, but it has a whole list of outstanding patches. And so with this, when you monitor this via Salt, for example, with SUSE Manager, you will see that something is not okay. Yeah. And that's also the reason that you need at least one person at the factory who is able to install a Raspberry Pi, because there's no IT service available at the factory. So some more internals here for the System D patch at boot service. So the most important here is really that the service is of type one-shot, and it's really type one-shot is a System D mechanism to, well, you could call it fire and forget. You execute a command, you will not see any service running in the background. It's just one application that's executed once and then it's done. And the implementation looks like this. So as we said before, you have to make sure that the time is set correctly. There's a command that's called cronC. And cronC tracking gives you back the status, so you can really grab for leap status. And if this is normal, you know that the time has been set from cronC. So and afterwards, you will know this command. So zipper is called with, yeah, it will respond with yes for every question that is asked. So we'll do everything automatically. So the last part that really needed reworking for this solution to work out is the auto login mechanism. And there was at some point an auto login which was functional in a way that it could be used automatically, but here we needed to do just some adjustments. Yeah. And mainly it's about the order, how to execute things. For example, here it's done to first start the browser and then the window manager. The onboard screenboard is necessary later on. And so maybe just some reasons why is an onboard screenboard needed at all. And the worker, for example, they need to log in sometimes at the station, or the ThingWorks application, it will probably show there's a next cleaning cycle that needs to be done. Or maybe just one other example, Adi, you mentioned barcode reader is also one of the peripherals used there. So if the barcode reader doesn't function well, someone needs to put it by hand to make sure you can continue with the workflow. But this is also a good thing that this allows for tweaking workflows also. If you use it in different factories and they have a different workflow, you can just use it then. Okay, here's some more internals with the auto login. So mainly only the one user can execute it. That's the 4755 with a change mod command. No other users able to execute this. And it's only started with one virtual desktop, and the a getty command. We were not sure a getty or a get tty, but at least the command is the standard console login handler, and maybe just some fun fact. So it's really alternative get teletype, yeah. Although teletypes were already out of date in the 1970s when this command was brought up. So just some fun fact. Okay, one more thing about the automatic login. This is all combined together, how you start the whole desktop. So again, you disable screensaver, you start the on-screen keyboard, and Midori is the browser which is started already with the right application. And then you need some initializations within the xinitRC. So xinitRC, for those not familiar with that, this is the place where, depending on the X environment, you can set environment variables for server startup. So then finally the desktop is started and it's reduced to one virtual desktop. And with this, back to you, Adi.
Next slide, please. Yeah, a MESkit shall be installed in a factories, as we heard. The factory service teams have normally poor Linux knowledge, but they are feeling more comfortable if they can do a self-installation. So the other side is we have no keyboard and no monitor on a lot of MESkits. So answering installer questions is not possible with this hardware. So an unattended installation is a must, but this is not covered by SUSE image for Raspberry. To solve all this, we can either use our own Kiwi image, which we do not actually, or modify the SLES image. For that, I wrote a SD-write script with, here you have to connect a card reader to USB, call a script with hostname, application, SUSE Manager channel to register, and if wanted, a URL to be initially displayed in a browser. And with option -W for Wi-Fi makes no sense in the MESkit contents. Next slide, please. This is the easy management slide. We really put SUSE image, Knorr extensions, and ADG software on an SD card, put the SD card into a Raspberry, connect the Raspberry to a network, power it on, take a coffee, and that's it. And that can also be done by factory service teams. Next, please. For a MESkit, we have a naming conventions. 3-letter site abbreviation, the word MESkit, and site-specific name, like production line name or so. The SD-write script is writing the image, is replacing queries by predefined answers in a SUSE first boot script. Then it is adding the SUSE Manager registration in the first boot script. And the trick is, SUSE Manager registration key is capable to define salt states behind it, and that completes the installation. And why the host name in the why the site in the host name? It is used for settings like keyboard layout, time zone, and also a site-specific time server, because Chrony does not take it from DHCP. Next, please. Why replacing UUID? It's a lot of work, can make troubles if something goes wrong. Yeah, the SLES image has a fixed disk UUID in it. And when writing the image for a new Raspberry from another Raspberry, both running the same image with the same UUID, it will get dangerous duplicates. So UUID conflicts must be avoided. And to be sure, replace UUID as soon as possible by a new random ID. In my case, it is directly after after image is written to the SD. So we are safe in this point, because the installing Raspberry has also a modified UUID, the initial installer. Next slide, please. Here are the steps happening after first power on. The patch SUSE first boot is registering at SUSE Manager. The finishing reboot is running into patch at boot. The very first patch at boot will normally install patches with reboot required. So in this case, the reboot will take place, and after a second reboot, the Raspberry is booting directly into application run. And all this is running unattended. Next slide, please. Here you have MESkit view in the SUSE Manager, as registration is the first step in the installation part. This view is available a long time before installation has finished. Let me say directly after a blank screen is coming on the first boot in script. So next slide, please. A few words to SD cards. The black standard class 10 card is normally sufficient for Raspberry Pi. If there's a lot of I/O intensive work or disk writing application or a lot of swapping, much logging or so, prefer a video 30 class. This is faster and even faster than with V30. Does only waste money because the Raspberry doesn't support this higher speed. Next slide, please. A word to security. We try to implement a certain security by design. In a factory floor edge, the Raspberries may open connections to ThingWorx for sending data and calling with HTML pages from the ThingWorx server, to SUSE Manager, using salt calls. Internet access is not allowed for Raspberries, and the Raspberries are not reachable from the corporate LAN. And finally, the patch at boot, even if it's modified or switched off, is reinstalled by the salt. And please go ahead.
Yeah, so with this, some final words on our presentation. So what's really good to know, because Ada, that you experienced it a few times, that colleagues of yours just wanted to use Intel code on Raspberry Pi, and this will not work. Yeah, so it's its own architecture that Raspberry Pi uses. That should be clear. Another thing is really, we talked about window manager and IceVM, for example. That's very common that you use the right mouse button to have the menu on top. This will naturally also not work. Yeah, so But you also have here with the left mouse button the possibility to have the application menu and just get everything from there. Yeah. So these are just some things, well, people basically just should be aware of, yeah, put it this way. Also, that's the UUID thing you mentioned. The SUSE Manager registration will just fail if the hostname is already registered, yeah, and if it's really not unique. And also, it's somehow slower than on Intel platform if you're using the salt command on Raspberry Pi, yeah. So this MESkit device is already used in production at some factories, also in different countries. So over more than 50 MESkit devices are used, and it's planned to use it much more. And yes, with this, we'd like to, no, not here. With this, we'd like to thank you for attending this virtual presentation at SUSECON Digital 2020. If there are any questions concerning how everything works more in detail or how things are used in the factory, you can contact us via email. But I also want to make sure to thank again ADG, the company who builds the device that is also used within the MESkit device, because it's really 3 companies together that made this solution possible. With this, okay, thank you.